How many wavelengths are displayed in this image? Waves with higher amplitudes always have lower frequencies. A sound wave has a velocity of 340 meters per second. A beam of light traveling at 3 times 10 to the 8 meters per second, very fast speed, 300 million meters per second. What is the difference between a crest and a trough? How many wavelengths are displayed in this image? It's somewhere between 1 and 4. So what's a wavelength again? It's the total pattern of the wave repeated. So we can see that we have a bump over here, and a bump at the bottom, and a bump at the top, and then a bump at the bottom. But this is not 4 wavelengths. One single wavelength is the entire repeated pattern. So that's one bump going up and one bump going down. So that means up until about 40 we have a single wavelength, and then up to 80 we have a second wavelength. And so our answer is simply 2 wavelengths. Question 2. We have some true or false questions. Waves with higher amplitudes always have lower frequencies. Now, what's amplitude a measure of? It's a measure of the total displacement of the particles. But frequency is a measure of how quickly the wave is moving through space. So what this means is that whether or not it has a high or low amplitude, it could have a high or a low frequency. So our answer here is going to be false. B. Waves with higher frequencies always have lower periods. Now, what was that equation relating frequencies with periods? F equals 1 on t. If t is very large, f will be very small. And if t is very small, then f will have to be very large. So in this case, it's true. Remember that the period is how long a wave takes to travel one wavelength, and the frequency is how quickly the wavelengths propagate, or how quickly the wavelengths pass through a particular point in space. So we can see just from that description that if we have a high frequency, that is, if a wave is passing through a particular point with many wavefronts per second, then the period, how long each wavefront takes to get through, will be very small. C. Waves with higher periods always have lower wavelengths. Now this is an interesting question. We know that if a wave has a high period, it will take a long time for a wavelength to travel through a particular point. And we know that if something has a low wavelength, then it will be very bunched up and together. But what we don't know is the speed of the wave. If the wave is traveling extremely quickly, then it might have, even if it has a very high wavelength, it might have a very low period. On the other hand, if the wave is traveling very slowly, then it will have a very large period, even if it has a short wavelength. So in this case, we can't really say. And that means that we can't say that they will always have lower wavelengths. Our answer then is false. Question 3. A sound wave has a velocity of 340 meters per second and a frequency of 256 Hz. Find its wavelength to 3 significant figures. I hope you remember your scientific notation rules. So how would we go about finding this? Well, we can use the wave equation. Can you remember how it goes? V equals F times lambda. So in this case, we're given V and we're given F, but we want to find lambda. So we need to rearrange our equation. We can see by dividing both sides by F that lambda will equal V over F. What we need to do now is substitute our V and our F. That gives us a value of 340 over 256, which evaluates to about 1.33 meters. So this is a rough sort of estimate for the length of a sound wave. Of course, different sound waves might have higher or lower wavelengths, but we'll learn more about that in a later section. Question 4. A beam of light traveling at 3 times 10 to the 8 meters per second, very fast speed, 300 million meters per second, has a wavelength of 500 nanometers, very small wavelength. Find its period to 3 significant figures. Now how do we go about doing this? Remember that the velocity of a wave is given by distance over time, wavelength over period. So the period is what we're trying to find. There's our equation. Now how do we make the period the subject of the equation? Well, we can multiply both sides by the period, assuming the period's not 0, and then divide both sides by v. That gives us this equation. T equals lambda over v. All we need to do now is substitute in our values for lambda, 500 nanometers, and v, 300 million meters per second. Now, we're given the wavelength in nanometers. What we need to do is turn this into SI units, that is, meters. Remember that the conversion for nano is that 10 to the power of minus 9 meters equals 1 nanometer. So, you can substitute in these values. 500 nanometers over the speed of light, which should give us its period. That'll turn out to be 1.67 times 10 to the minus 15 seconds, which is an incredibly small amount. Beams of light have very, very small periods, and it's often more useful to measure them in terms of their wavelength than in terms of their period. Question 5. What is the difference between a crest and a trough? Now remember, crests and troughs are both points of extreme displacement, but they're in different directions. Can you remember which one goes up and which one goes down? The crest has the maximum displacement, so it's displaced in the positive direction, which is normally up on a graph. A trough, on the other hand, has minimum displacement, so it's displaced in the negative direction, so it's down on the graph. Right, so that's the end of the questions. We've gone over several different wave terms that we can use to describe waves, things like velocity, frequency, wavelength, period, amplitude, intensity, that sort of thing. And we've gone through some questions that make sure that we know exactly how to use them. In the next section, we'll be talking about graphing these properties of a wave.